Okay, let's get started again. Let's go to the notebook. Okay, so now we know how to build model, how to make confusion matrix, and then how to calculate the accuracy matrix. And then now there are a few. This code is for plotting the distribution of predicted probability. Actually, in practice, you don't really need to make the plot. Okay, the plot is just to help you understand the underlying mechanism, right? So in practice, you don't really need to make the plot, right? So the plot is just for, but making the plot is like easy, right? So you basically just put you make a data frame of y and actually the predicted probability, isn't it, right? And you use the y as the color, and you use the x, right? Because you want to make histogram, right? So you simply build a histogram on the predicted probability and use the actual value of y as color, right? That is easy, right? So it's easy to make the distribution of predicted probability. It's quite easy. And this is for training, right? I left the testing part for your own, for your homework assignment this week, okay? And then ROC and AUC. Now in the MIT course, it actually has a very lengthy process to make the curve, right? But nowadays, you don't really need to do that, okay? Today we have, in this package, in this CA tools package, you actually have the function to, plot the ROC curve and calculate the area under curve in one function call, okay? I mean, in the MIT course, it actually do a lot of function to draw the curve and actually calculate the AUC, right? You don't need to do that anymore, right? Today you only need to call one function, and in this function, you would actually plot the curve and calculate the area under curve in one function call, okay? The way to call the function call is called column AUC, and you give it the predicted vector, the vector of predicted probability, right? And this is the actual y value, see, okay? And then you tell the function whether you want to make the plot. If this is true, then you will make a plot and return the area under curve, okay? If this is false, it will only return the AUC, okay? So today, to draw ROC and AUC, it's a lot easier than before. Okay, so R is an environment that it evolves time after time, right? So the things for business analytics is getting easier and easier, and it's getting better and better because they are new model, so you can make a better prediction, okay? And you only need to learn R once, but as the package evolve, your capability of analytic would like grows with time, right? Okay, so this is a way to calculate the training AUC and the testing AUC, right? You can compare them, right? You can compare them. Now there's one more thing that I want to explain for AUC. Where is the slide? Now AUC is actually mathematically AUC is quite the term area under curve, it actually has a practical implication, right? It implies that if we randomly select one point from each of the two classes, the ratio that the model can correctly discern the two, can separate the two, can accurately separate the two. Okay, let's go to the simulator. Okay, so now you have this predicted probability, right? The distribution predicted probability. If I randomly select one point from the rate, which is actual 1, okay, and I randomly select another point of y equal to 0, right? So if the first point's probability is higher than the second one, then I will say that the model correctly separate the two, right? So if your model is very good, right? Your model is like this. This is the simulator, right? It's not actual, but if you have a model like this, right? So whatever point that I select from this one, its predicted probability must be higher than whatever point I select from this one, right? That in that case, you can see that the area under curve is equal to 1, right? Isn't it, right? Because there's no probability that it would mix up, that you would get wrong prediction, right? But if your model is like this one, as you can see that as the two distributions start to overlay with each other, the curve, like the area under curve, just start to drop, right? See? Okay. So how can I make as you can see that if I put this lower, okay, is the AUC increase or decrease? If this is actually the value of the red distribution, right? So if I move it downward, as you can see that the AUC dropped, right? And if I put it upward, see, it's separated. The capability that the model can separate the two classes, okay? That's basically what AUC means, okay? The extent that the model can correctly separate the two classes, okay? That's what AUC really means, okay? The mathematics things is that like I don't want to cover it in this course because it will take too long, okay? But you only need to remember the things, right? The reason that we want to use AUC as a measurement of the performance of a model is because that in business situation, a good model is the model that can separate the two classes, right? As much as we can, right? The higher the AUC is, the higher, the better that the model can separate the two classes. Okay, as you can see here. If I then the AUC will like increase to what? Is that clear? Okay, so you only need to like learn the practical implication of AUC, and that's important. Okay. Now let's get back to our notebook. At the end of 11A, there is a quiz. Okay. In this notebook, I only use two variables to make the prediction. Okay, but actually in our data, we have 14 variable, right? This is pool care. This is the target variable, and this variable is not useful because that's just the member ID, right? So you actually have 12 variable, 12 predictor that can be used to predict pool care, right? Okay, so I want you to I want you to do this. Using all of the column, right, except member ID, to build a model that predict pool care. Okay? So it's not just the two variable. I want you to use the 12 variable to predict pool care. And then, again, create the training and testing confusion matrix, calculate the accuracy, and draw the distribution of predict probability. Okay? Basically, just follow the notebook. Just do it again. And then estimate the AUC. So is the model more accurate? Is the model of 12 predictor better than the 2 predictor model? Would it be better?
No.
Why? Why
Too many
is?
variables.
Sorry?
The more the variables, the more the uncertainty.
Is that true? The uncertainty will not change. Uncertainty is still the uncertainty. The more variable you have, the more information that you can use to predict the problem, to predict the outcome, isn't it? Uncertainty will not change with the number of variable you use. Right? The uncertainty is the uncertainty. The predictor that we are using is we want to using the information in the predictor, try to explain the variation, isn't it? So if I can use the information in X to predict Y, then some of the uncertainty in Y would be controlled, isn't it? That is the idea of modeling. So usually the more predictor we use, the more accurate the model is. Okay? You can do the comparison yourself and see how it works. Okay? So this is one of your homework this week. Got it? Question? No? Okay. Now, if no question, then let's go to notebook B. We are starting to do, this is do prediction, right? Now we want to do decision. Okay. Yeah. Again, there are some formatting codes, and I build a model. Okay, so these two code chunks are the same, exactly the same as in 11A. Now this is the prediction and decision process that we are going to do. Let's take a look at the slide first. Now, as I say that after you do the prediction, what you have is actually the distribution of the probability, right? Then you add a cutoff, then you get the confusion matrix, right? Predicted probability plus the cutoff value, the threshold, then you get a confusion matrix. And the confusion matrix actually would change with the cutoff, right? Right? That's what we learned so far. But when we are making decision, what is the purpose of making decision? Usually in a business scenario, we want to make a decision that would lead to the maximum expected payoff, right? Right? In business, usually we want to make a decision that will lead to the optimum or maximum expected payoff. Okay. So what is the ratio of action, right, would lead to the largest expected payoff? Basically, this is the question that I want to answer, isn't it? Yes.
You said it's 0.5. Like for decision, we use 0.5 threshold.
That's for
Decision.
accuracy. That's to maximize the accuracy of the prediction, right? 0.5 would usually maximize the accuracy of the prediction, but sometimes accuracy will not lead to optimum outcome. Okay, why? Because every business has a different payoff condition, right? Yes.
So by payoff, you mean that we want to increase the positives.
Sorry?
Expected payoff, like increase in expected payoff, doesn't mean that we want to increase the positives.
Yeah, accuracy would not lead to.
Increase in positive, like the predicted positive and the actual positive. We want to increase that number.
I will explain that later on. Let me finish this slide. You'll actually answer your question. Okay. Let me finish this slide. Okay. So as if I have a confusion metric, I actually do not know what is my expected payoff, right? How can I calculate my expected payoff? I need to know that for each of the case, right? For the true negative, false negative, true positive, and false positive, for each of these case, how much payoff would I have, right? In the case of diabetes data case, okay, in that case, now if the actual poor care is 0, okay, so it's good care, and let's take the threshold as the threshold for action, okay? So this is no longer negative positive. Instead of negative positive, this is no action, this is action, okay? So if it's good care, then I don't need to take any action, right? And if there's no action, there's no cost, right? Isn't it? So if it's good care and I do not take any action, then my payoff is 0, okay? And if it is good care and I take the action, then I need to pay the cost, right? Because I make the action, so the action has a cost. Maybe I just give the patient a drug or something, right? A medication treatment, right? And so this is the cost of treatment, okay? So if it's like good care and I do the treatment, then I need to pay like 10, okay, 10,000 or something like that, okay? So now in this case, if it's actually poor care and you do not take action, okay, that's the worst, right? He is actually poor care and you decide not to take action on this patient, right? So because you are insurance company, right? So from your historical record, you should be able to calculate in average, poor care people would cost you a lot of like cost of risk, right? You can say it that way, right? In average, if you do not take action to these poor care people, it would cost you like 100,000 in the future. Okay? So this is the thing that you already know, right? But actually, if he's poor care and you take action on him, right? You can reduce the risk, right? But you cannot reduce it to zero, isn't it? Okay? So in this case, if I can reduce the risk from 100 to 50, okay? Okay? And plus the cost of action, okay? Because I take action, so I take 10,000, right? But I can reduce his cost from 100 to 50, okay? So in this case, my net payoff is like 60, okay? And because they are all cost, so this is like preventive medication is kind of cost reduction action. So all of the payoff metrics are negative, right? So this is the worst case, right? He's actually poor care and I do not take action. I want to reduce the cost, okay? So if I want to reduce the cost, but the action has a cost by itself, right? Okay, so this is the payoff metric in this specific business environment, okay? And that condition will change case by case by case. Every business scenario would have a different payoff metrics, okay? And this metric is not coming from the model, not coming from the data, right? It's coming from your daily operation, right? It's coming from your domain knowledge. It's coming from your business condition. It's coming from your business logic, right? So only manager knows these metrics, okay? So you can have an engineer build a model for you and do the prediction for you, right? Okay? But before you have this payoff metric, you do not know how to calculate the expected payoff, right? So say you have a confusion metric and you have a payoff metric. It's easy to get the expected payoff, right? Okay? This is the frequency of the four type of event, right? And this is the payoff of the four type of event, right? You have the frequency and we can treat frequency as probability, right? So you have these two metrics, you simply like multiply the four element and then do the sum of product. And that is the expected payoff, right? And this is the thing that we want to maximize.
So the confusion matrix comes from the data, but
Yes.
the payoff matrix is something that the company.
Yeah, as a manager, you should know, okay? Right? And you need to combine the two to calculate the expected payoff, okay? Now there is still one thing left. Because the confusion metric will change with this cutoff, right? Okay, so which cutoff should you use? That's what programming can help, okay? We can do a simulation, right? We do not know in advance that which cutoff is better, right? But we can like write a program and I simulate cutoff equal to 1, equal to sorry, 0.1, 0.2, 0.3, and all the way from 0 to 1, right? I scan all of the cutoff, right? Now, each of the cutoff would produce a confusion metric, okay? And each confusion metric will lead to expected outcome, right? So as long as you know this, as long as you have a model to help you do the prediction, then you can always write a program to find the best cutoff that lead to the optimum expected payoff, right? It's got the point? Question? Okay, let's do it with the real data. Okay, let's do it with the real data. See, this is the to plot the DPP, the distribution of predicted probability. As I told you that you don't really need to plot this. Okay, this is just for explanation purpose. Okay. In real action, it's like before you can estimate the expected payoff, you need to define the payoff metric first, right? See, and the payoff metric is made up of like Tn, the true negative, false negative, true positive, and false positive, right? So in the diabetic case, it means that true negative is no action, good care. Okay, it's nothing. And false negative is like is poor care, right? But I take no action, right? And that's very bad, right? It's the average risk of poor care. Okay? And then if it's good care and I take action, it's the cost of the preventive action, right? And then if it's poor care and you take action, right? And you need to pay the cost because you take action, okay? But the risk will be reduced, the reduced risk after taking action, right? So that's the payoff metrics that you need to prepare before you can calculate the expected payoff, right? Okay. So the expected payoff will be calculated as in this way, right? You like multiply the two metrics, payoff and confusion metric, and do the sum. So it's easy, right? It's not difficult. It's not difficult at all. That's why we want to learn programming as well as probability, because as long as you can combine the two, then you can do a good decision, good business decision, right? Now let's see the way that we define our payoff metrics. Okay. Okay. So so this is the payoff metrics. Okay. So the way we define the metric is like you need to supply the value, right? Be careful, though, the order is this way, right? You want to change the vector of 4 into a metric of 2 by 2, right? In this line of code, I actually change the vector of 4 into a metric of 2 by 2, and then that's the way we do it, right? And the name is just to like give it a label. It's not too important at all. Okay. Now let's take away that how we can estimate the expected payoff for each confusion metric derived from each threshold of action. Okay. Now we want to first of all we set a cutoff as a sequence from 0 to 1, and every step is 0.01. So this is, so cutoff is actually a vector of, what is the length of a vector?
0 to 1.
No, the length of the vector. How many elements are there in the vector? It's from 0 to 1, and every step is 0.1. So it's 0, 0.1, 0.2, 0.3.
It will be 0.01, 0.02.
Yeah.
So that's small.
Yeah. So the length of the cutoff is like 101, right? 101. So this is what we want to calculate, because the R will do the calculation for us, right? So we can actually, first of all, define the cutoff, right? And then we call as applied, right? Yeah.
Professor, wouldn't the length be 1,001?
Sorry?
The length will be 1,001.
1001?
Because it's 0.01, 0.02, 0.02. Oh, sorry.
Okay. You got it wrong. Okay, you got it wrong. Should be 101. Okay. So now I use as apply to apply the cutoff to this function. Okay? So for each element in cutoff, I call function. Okay? And in this function, first of all, I calculate the confusion matrix. Okay? And then I multiply the confusion matrix with the payoff matrix. Okay? And then sum them up. Okay? And well, look at the way that I build the confusion matrix is a little tricky, right? Now, first of all, I'm using like y equal to 1, right? Okay, and I convert it into a factor. Okay, so well, usually when you are doing the confusion matrix, when you are simulating a confusion matrix with a real data, you want to convert the value of y into a factor. Okay, you want to convert the prediction into a factor. Okay, so otherwise the table might reduce to like the table should be a 2 by 2 table, right? Okay, and if you do not convert the two variable into factor, sometimes you would reduce to like 1 by 2 or 2 by 1. Okay, that type of things, and it would there will be error in this as apply function call, right? So the only complication is that when you do the confusion metric, remember to like impose the data into factor, right? Okay. So again, so the table would create the confusion metric, and then you use this to calculate the expected outcome. So after I call this as apply, corresponding to each one of the cutoff, there will be a result, right? So after I run results, I will have how many results?
101.
Yeah, 101. Okay, so now you have a cutoff, you have a result. You just make a plot. Okay, this is the cutoff, and this is the result, right? The rest of it is just the plot. Okay, I plot this as x, plot this as y, and I find the maximum point, put the red dot there, right? And the position of the red dot will be put it here, right? It's so for all of the cutoff that I simulate, the cutoff that will produce the maximum accepted outcome is cutoff 0.16, and it will produce expected outcome of minus 2360. Okay. As I said again, because predictive medication is a thing about cost reduction, right? So the expected result is always zero. It's always minus. It's always negative. Okay. You just want to reduce the negative number, right? That's cost reduction type of thing. Okay. So as you can see that after this calculation, okay, we can see that if we take action to all of the patient with the probability of poor care more than 0.16, I will have the optimum expected payoff, right? And that's what we want, right? And this is basically the process of from prediction to decision, right? The prediction gives you the distribution of predicted probability, okay? And for decision, you need to know where is the cutoff, which cutoff will lead to the best expected payoff, right? But in order to do that, you need to specify your payoff metrics, which come from your experience, come from your domain knowledge, come from your sense of business type of things. Let's get it? Okay. Any question up to this point? No question. Okay. So now, as you can see that the simulation is kind of choppy, right? It's kind of like choppy. That usually when you are doing a real business case, the line will be a lot more smooth than that. Okay. Because we are using a very, very small sample, right? The sample is only like 100 point something, right? So there are two little samples, so there will be a lot of noise, right? So in the following code, I try to extend the data set to 10K, okay? You know, I mean, in the beginning, the data set is only just 130 point, okay? So I use some technique, okay? Try to extend the data set to 10K, okay? And then I do the same thing again, okay? So now it's a model. The data is called. I build a data frame called A, okay, and let me run to. So D is very small, right? So I create what? So I create another data frame called A, okay? So A is like a lot larger. It's like 10,000 point, right? So, and I do the same thing again, right? So as you can see that I build a model, right, out of A, okay? Now the A has like 10,000 point, okay? So, and then I do the simulation again. Now the simulation curve is a lot smooth than, right? It's a lot smooth than, it's no longer very choppy, right? So usually this is the case when you are in the real business situation, because you always have like thousands, tens of thousands, maybe millions customer to do it, right? So okay, so this is the simulation. I simply like enlarge the data to show you that the case that we will see in the real business environment. Okay. Now it's not just here. Okay, we can actually do one step further. Okay, we can actually do one step further. Now let's take a look at here. We can actually do interactive simulation. This way of programming, we call it simulation, right? Because I simulate, I select a range of cutoff, and I do a simulation of each one of them, right? And I plot the result. Simulation, we can make the simulation interactive, okay? In our file folder, there's a code called sim11br, okay? Just open the file, and then let's execute the file. Okay. As you can see, that to steer the simulation, but here there's a gear, okay? So you can pull out the gear. As you can see that now I can adjust the payoff matrix interactively. Okay? In this simulation, okay, the payoff matrix is fixed, right? It's fixed, and it's like this one. Okay, it's fixed. The payoff matrix is fixed. Okay, but in this code, I kind of like use a slider so that you can like interactively adjust the payoff matrix. Okay, to see how the result of simulation change with the payoff matrix. Okay, so for example, usually we do not change these two, right? Because there's no action and good care, right? So it should be fixed at 0, right? And for this one, it's like no action, and actually it's the average cost of risk, right? Okay, so usually we do not change these two things. This is the cost of the action, right? So if the cost of action increase, what will happen? We can see, right? What happened when the yeah, the cutoff would, when the cost increase, the cutoff increase. Why? Because if the cost of action is higher, okay, then you tend to take action on more or few people. No, the cost increase. Cost increase, so you don't want to do it on too many people. So you apply the action to fewer people, isn't it? That is the logic, right? So if the cost decrease, then you're applying to, these are the people that you apply your action, right? And these are the people that you do not apply, right? Because you set the threshold, and above the threshold you apply the action, right? Isn't it? Right? So if the cost of action like decrease, as you can see that if the cost decrease to like $5, you actually should apply the action to all of your patients, isn't it? right? And if the cost is very, very high, what will happen? Oh. I'm not sure it's still working. Okay. As you can see that as long as you can reduce the risk of cost, right? Still you have someone that you can apply, right? So this is the thing that adjusts the cost, right? And you can actually try to like if the this slider kind of like determine the effect of the action, right? If the effect of the action is better, should I move the slider this way or this way?
Sorry, effect of?
Yeah, if it has a better effect, I mean if it can reduce the risk, the extent that you can reduce the risk, if it can reduce the risk like lower, right? It means that they have better, right? The effect of this drug is better. So, for example, if as you can see, that will jump up, right? See, because the action is like it can reduce more risk than this way, right? This is what we mean by interactive simulation. Okay? It's not only that you can fix the payoff matrix and do a simulation once. You can actually use the slider to like adjust different business condition. So you can kind of examine how your decision and how the corresponding outcome would change when your business condition is changed. Right? Let me say it again. Interactive simulation can help you understand that when your business condition change, right? How is your optimum strategy and the corresponding outcome change with your business condition, right? Okay? So this is the power. This is the power when you can combine probability and programming together. But programming and probability is not enough. The point is you want to combine your sense of business, your business logic, and your business experience with probability and programming. And that synergy is what I have shown you now. Okay? And it's what we want to learn in this course. Okay, it's 11 o'clock already. Let's take a 10 minutes break. Okay, we will be back at 11, at 10 after 11. Okay.